Okay, so we have two review questions for the Chapter 14 test. Here's the first one, the 2005 question about pendulums. So the first thing we have to do is a free body diagram at various points in time of the motion. So we have at point P, we have our pendulum bob, and point P is off to the left of equilibrium. We have to draw the forces that are acting on it and give them good labels. So the first thing is there's a tension. Since we're not at equilibrium, the tension's pulling kind of up and at an angle to the right, because that's the direction the string is at. And then we have, actually I'm going to draw that a bit cleaner, at the weight, right? So that's at point P. At the bottom, we still have the pendulum bob, and the forces acting haven't changed, but the directions have. The weight remains straight down, and the tension is now straight up. Realistically, for both of these, the length of the tension vector should be longer than the weight vector, but that's not something that was scored. They weren't that critical about it. You just need to have the directions and the fact that those are the only two forces. So that's part A. Part B, we need to figure out the speed at the lowest position. And this is going to be easiest done with energy conservation because we're told how high it is above the lowest position at points P and Q, the maximum amplitude points. So we can set up a sort of energy is conserved statement and write that the energy before equals the energy after, where before is at point P and after is at the bottom. So at point P, it's not moving, so it has zero kinetic energy, but it has potential energy mgh. Given the value of h, that's the 0.08 meters. And after, we've put it at the zero of our gravitational potential energy, but now it's moving, so it has kinetic energy 1/2 mv squared. And so if you don't know exactly how to solve everything, fine, but noting the energy is conserved alone is worth some points already. So we set up that, now we just need to solve. Right? So the masses cancel. If we multiply by 2 and take the square root, we're going to get v equals square root of 2gh, and g is 9.8, and h is 0.08, right? And so we plug all that in and solve, and we get 1.3 meters per second. So that's part B. How fast is moving at the bottom? The next step is going back to circular motion. So we need to know the tension in the string when the bob is at its lowest position. Well, we have the free body diagram for that set up. So we only have vertical forces, so we're going to write that the vertical forces sum is mass times acceleration. But a pendulum is right, circular motion. The bob is moving in a circle. It's not getting all the way around the circle, but it's moving at least in part of a circle. So the acceleration we have is a centripetal acceleration, right? And we know the equation for centripetal acceleration. If you don't remember, it is on the AP sheet. And then the acceleration v squared over r. In part B, we just found v squared. And r is going to be the length of string, right? That's the radius of the circle that we're moving in. And our free body diagram tells us what the net force is, right? It's tension minus mg equals mv squared. I'm going to replace r with L, the length of string. So to solve this for t, right, we get m g minus v squared, g plus v squared over r, right? And now we have all those numbers. We know the mass, 0.85 kilograms. We know g. We know v is the 1.3 meters per second. And again, if you got the wrong velocity in part B, use whatever you got and you'll get the points in part C. And then, oops, as I realize now, I went back in notation here. So this, right, this is L, the length. As we plug all those numbers in, length is 1.5 meters, and we get 0.93 newtons. All right, so that's the tension that's needed to keep it moving as it is. Okay, so that's part C. Part D, describe one modification that could be made to double the period of oscillation. Well, we know what the period of oscillation of a pendulum is. Right? 2 pi times the square root of L over G. So if we want to make this into 2t, we can either modify L, right, that's one option, or we could modify G, right? 2 and pi are constants, those aren't changing. We notice that L is under a square root, so we want to make this whole thing twice as big. We have to make L 2 squared times bigger, right? Because if we take the square root, then we get the factor of 2 out. So if one option that we have is that L turns into 4L, right? That would be one way that would fix it. That would make the period twice as big. The other option, we can do something similar with G, but it's in the denominator. So we need to make G into 1/4 of G. So, right, we could either make the string 4 times longer or find a planet where gravity is 1/4 as strong. Either one of those would work. The length is probably the more obvious option. All right, so this last was a extra part I added because this was a short question. And asking about the amplitude of the motion. We know how much the height changes by, but that's not the amplitude, right? The amplitude is either the angular amplitude, the theta that's drawn in the picture, or the arc length s. And either one of those answers would be acceptable. Those would answer what the amplitude is. But it's not the height. That's not the path the pendulum is actually moving in. And so you can give an answer in terms of like degrees or radians, or arc length, which will be meters. And there's two different ways that you can approach this, which are really the same thing, but one of them requires you to memorize an equation, and the other one would require you to do some geometry. So I'm going to do it both ways to show you. And actually there'll be a difference at the end that I'm going to talk about as well. So the first is we've derived an equation in class that related the maximum velocity to the amplitude, right? 2 pi f a. And the frequency is 1 over the period, so 2 pi a over t. And we can calculate the period because we know the period is of a pendulum, right, is what we kind of mentioned earlier. We didn't calculate it earlier, but we know we could get those numbers where we have L and G. And we found Vmax, right? That's the velocity in part B. And so if we put all that together, right, so we get an A over the square root of L over G, which is kind of an ugly way to write it, right? The 2 pi's would cancel. That's why I didn't put them in there. So this is also A times the square root of G over L. And we want to solve, well, actually, I can even make this easier. We don't need to do this step. So we want to solve this for Vmax, or sorry, for A. So we're going to multiply both sides by the square root of L over G, L over the, or rather, multiply both sides by the square root of L over G, right? Which cancels all that, and so we get A equals the square root of L over G times V max. And those are all numbers that we know. And if you plug those in very carefully, you get 0.51 meters. And that's an arc length, right? That's not an angle. So this would be the answer for like how far it travels sort of from the bottom of the circle up like that. This would be the 0.51 meters, that sort of distance. So that's one way, if you happen to remember this relationship from what we've done in class. The other option is more geometric, right? So the pendulum, the string length does not change. So this length is L, and this length is L. and the angle between them is theta. Right? So if I kind of carefully draw in a right triangle, we know that this, I'm going to keep changing colors, so we know that this is the 0.08 meters, and specifically we know what L is as well. This is the 1.5 meters, right? So if I want to figure out the length of this bit right here, I can use a relationship with cosine. Right, we know the hypotenuse, we know the angle, and we're trying to find the adjacent side. So cosine theta equals the purple bit, which I'm going to call y, right? Whatever that is y, all divided by, right, L. But what we need is something a little bit more involved. That's a step, we need a little bit more. The other thing we have to recognize from this drawing is that there's a relationship between the orange height that the pendulum bob moves up, the total length L, and the little bit that I boxed in purple Y. And that is this, that, actually, let's write it this way, that L is Y plus 0.08, right? If you add all those two pieces up, you get the total length. So we don't know what Y is, but we do know what L is, so we're going to get rid of Y in that upper equation. So this is L minus 0.08 all over L. And so if we want to solve for what theta is, right, that's an inverse cosine. So then theta equals cosine inverse of 1.5 minus 0.08 all over 1.5. If you plug that into your calculator, you'll get 18.8 degrees, or 0.33 radians. And so this would be an amplitude in angles. That's like an angular amplitude. That would also be a correct final answer. So you could leave it like that, or, as I'm going to go to the next slide, you can convert from an angle to an arc length distance using the definition radian is. Right? The definition of an angle in radians is the arc length S equals, in this case, L, the radius of your circle, times theta. And so we know L and we know theta. Right? This is 1.5 and this is 0.33. And if you plug that in, you're going to get 0.49 meters for the arc length. So this would be another acceptable answer. So now, you might be asking, well, I found an arc length in my first definition that was 0.51 meters, and here I found one that was 0.49 meters. Those are different numbers. And the reason is the small angle approximation. Is this equation right here describes simple harmonic motion, and the pendulum is only truly simple harmonic motion if the angle is small. And our angle, as you see, is about 18 degrees, and the small angle approximation really only works well below about 10 degrees. As you can see, it's still not terrible. I'm only off by 2 centimeters of my amplitude, but it's not a perfect agreement anymore because the assumptions that we used for simple harmonic motion aren't exactly true. So any of those four answers, 0.51 meters, 18.8 degrees, 0.33 radians, or 0.49 meters, are all really acceptable answers to this oscillatory motion question, since we're told that the amplitude is small, so that previous equation is allowed.